So Kepler's first law says that all planets move in elliptical orbits with the sun as one focus. So if we've got our ellipse here, we'll pop our sun in at one focus and voila, we have the orbital path of a planet. I will also define here two more useful terms that we'll need to know now that we know the orbit is an ellipse. We have the perihelion, which is the closest point the planet will get to the sun, and we have the aphelion, which is the farthest. You may remember that one of the problems that Newton had with his law of gravitation was that it did not predict that the orbital path of the planet would change slightly with each orbit. It was called the precession of the perihelion. So now it's clearer to see what that was. The perihelion, which is the closest point to the sun, changes very slightly with each orbit as the direction of the ellipse shifts very slightly. The final point I'd like to make on this page is that if we do choose to approximate an orbit as circular, we do so by using the average distance from the sun. So we said that the orbital radius is the average distance of the planet from the sun. Kepler's second law states that a line connecting the planet to the sun sweeps out equal areas in equal times. So looking at our orbital diagram again, if the planet is initially at this point, then after a time interval dt it will have moved. The area that it will have swept out is defined as the triangular or the approximately triangular area between the maroon and the red lines. And as the planet continues to move, for example to here, the area it sweeps out is now defined as the area between the red and orange lines, and so on. And Kepler's law says that each of these areas is equal. So that allows us to discover a few interesting features of the orbit. If the area doesn't change with time, then the angle that the area makes with the sun in each sweep must change. So the rate at which the angle changes, or the angular speed of our planet, will be changing. It will be travelling fastest at the perihelion, when it's closest to the sun, and it will be travelling the slowest at the aphelion, when it's furthest away. And this law also allows us to investigate what happens to the angular momentum of the planet. So here I've just moved the planet to a different point in its orbit to make the diagram clearer. So our planet is a distance r from the sun and at an angle d theta. We know the planet is moving with a velocity, and we know that the direction of that velocity is perpendicular to the radial direction. So that is, the angle between our velocity vector and the radius should be 90 degrees. So that means we also know, since the linear momentum of the planet is equal to the mass of the planet times the velocity, that the linear momentum is in this direction as well. I'm going to call the small area of this wedge dA, so it's the wedge between the major axis and the radial vector. And from Kepler's second law, we know that the rate of change of this area, dA dt, is constant. From our diagram, we can approximate this area of the wedge as a triangle, so its area is equal then to half base times height. We approximate the length of the base as r times the change in the angle theta, d theta, and the height by the radius r. These approximations are valid for very small angles of theta, and I've provided a link to a proof of this in the resources section on this page. And the approximations become more valid the smaller we make our angle theta. So to get a very small angle theta, we only look at a very small time interval dt. So in our time interval, the rate of change of our area is equal to half times r squared times d theta dt. So times the rate of change of our angle theta. We're interested in our angular momentum. So I will rewrite this equation in terms of our angular velocity to get that our change in area as a function of time is equal to r squared omega. So since we're interested in the angular momentum, we know that the formula for our angular momentum is equal to r cross p. And if that's unfamiliar, I would suggest going back to have a look at rotation and torque. In our case here, these two vectors are at right angles, so the cross product is maximum, and we have that our angular momentum L is equal to r times p, which is equal to r times m times the tangential velocity. Again, since we're looking at our angular momentum, I'd like to rewrite this equation in terms of the angular velocity, which gives us that our angular momentum is equal to m times r squared omega. So if we now combine our two equations, that is our expression for the rate of change of the area and our expression for the angular momentum, and we rearrange them, we get this equation here. So our rate of change is proportional to our angular momentum. So if our rate of change of area is a constant, then our angular momentum must also be a constant. That is, angular momentum is conserved. Kepler's third and final law is that the square of the orbital period t is proportional to the cube of the semi-major axis of the orbit, which we've called a. The derivation for this law for an elliptical orbit requires a slightly longer and slightly more complex mathematical derivation. So here I'll just derive the law for the circular orbit so you can see the process, and I'll generalize it to the elliptical orbit. I'll provide also a direct derivation for the elliptical orbit at the bottom of the page. We know that the force due to gravity on an object is given by Newton's law of gravitation, which is gm_m1r squared. We also know that for a circular orbit, that force is equal to the centripetal force, which we can write as mr squared omega. The angular velocity, omega, is related to the orbital period t as the distance divided by the time, so speed equals distance divided by time. And for a circle, that gives us that omega is equal to 2 pi divided by t. These should be familiar formula from the circular motion topic. So if we combine these two equations and rearrange, we find that our orbital period squared is equal to a constant 4 pi squared on gm times the radius of our circular orbit cubed. We also know that a circle is a specific case of an ellipse, and in a circle, the radius is the equivalent to the semi-major and semi-minor axes of an ellipse. So I'll show you this in that derivation at the bottom of the page, but for now it's enough for us to know that they're related, and consequently for an elliptical orbit, we can replace the radius term with the semi-major axis A, which gives us Kepler's third law. So in the previous video, we derived an expression for the potential energy of an object in a gravitational field from Newton's law of gravitation, and Kepler's laws allowed us to show that the tangential velocity of a planet changes during its orbit, which means its kinetic energy must also be changing. So in the questions following this video, there'll be a couple of questions looking at the relationship between the energy of the planet and its orbit.